Hello, I'm Mr. Howard. In this video we're going to be creating polynomial functions, and given the roots and any other point on the graph of a polynomial, it is possible to write the polynomial function. So that's exactly what we're going to do today. So in the following examples, use the given information to write the polynomial function. Make a sketch of the function if not already provided. Alright, so in this first example they give us the graph, and they say here that a cubic function contains the point -3, -30 and produces the graph shown below. Confirm your solution with a graphing calculator. Alright, so for my students, we need to do all of this work algebraically, and then we could just check it with a calculator. So the first thing that we have to do is identify the roots. So we have single roots here, here, and here. Okay, so 3 single roots. So we have, we'll write that here. So single roots at x equals -2. This one's at -2, -2. I'll just label these on here, -2, and this one is at +2. So x equals +2 right there, and then +3. So we have 3 single roots here. So we can already go ahead and start writing this as y equals, or f of x equals, either way, y equals some a value that we don't know for sure yet. It might be 1, but we don't know that, so we've got to work this out. So y equals our stretch factor there of a, and then if we have a single root at x at -2, that's going to be x plus 2. Remember, we write these opposite. This is opposite of what the root is, because x plus 2 would have to be equal to 0. You solve that and you get -2. So it's always opposite of this. So x plus 2 here. This one's at +2, so that would be an x minus 2 factor. And we have a root here at 3, so that would be an x minus 3 factor. All right. Now this is our second lesson on polynomials. You should watch the other videos on polynomials from lesson 1 if you haven't done so, where we identified the different types of roots, and that's how we already know here that these are single roots and how to identify them. And then we also talked about end behavior, and we talked about sketching graphs of these things. So you would need that background information before you delve into this lesson. Alright, so far so good. Now we take this point that they gave us right here, -3, -30, and we substitute that in. So we're going to substitute in a -3 for all of these x's, there, there, and there, and we're going to sub in the -30 right here for y in order to solve for that a value. Okay, so that's what we're about to do. So that would be -30 equals the a value we don't know yet, -3 plus 2, just subbed in the -3 for the x, -3 minus 2, subbing in -3 for x, and -3 minus 3, again subbing in that -3 here for the x. Alright, so simplify this a little bit. So -30 equals a times -3 plus 2 is -1, times -3 minus 2 is -5, times -3 minus 3 is -6. So that would be -30 equals a times -1 times -5 is 5. 5 times -6 is -30. So divide by -30 and we're going to get a equals 1. Alright, so in this case a happened to be 1, but it's not always 1. So we had to check it. So we're going to write it. We were using y. I'm going to use f of x now. So f of x equals, we can put the 1 here or leave it off. I'm going to put the 1 here. It's implied to be there if we leave it off. It would be fine if we didn't actually write it there. We just left this alone, left it off. It would be fine. X plus 2, x minus 2, x minus 3. Okay, and notice this is a cubic graph like they said, and we have end behavior up to the right. So as x approaches positive infinity, it's going up. As x approaches negative infinity, so the left side of the graph, it's going down, just like we would expect a cubic to do. I have gone ahead and put this in the calculator so that now we can actually graph this. And I've got that in y equals, and we've got it graphed here, and it looks like this picture. We can check some points also. So again, algebraically for my students, I want to see this, and then you can use your calculator to check it. So if we look in our table, that's a pretty easy way to look. I'm going to set my table up. We need a 0 of -2, so I'm going to start my table at -2, go up one at a time, look in the table. When x is -2, y is 0, that's what I expect to see. When x is 2, y is 0, that's what I expect to see. When x is 3, y is 0. Okay, those all check out, and I should also have the point -3, -30 in my table, so check that out, and it's there, so we know we have done this correctly. All right, so let's look at the next example. All right, here on example 2, we are given that a cubic function contains the point -4, 3 and has a double root at -3 and a single root at 2. All right, so we know it's cubic, so we know the end behavior, what that's going to look like. We're not given a graph here, so we're actually going to have to write the equation and make a rough sketch of the graph. Okay, so let's get started here. We know we have a double root at -3 and we have a single root at +2. Okay, so we know that this is going to be y equals, or we could say f of x, I'm going to use y here. So y equals a stretch factor that we don't know yet. Remember, we've got to find this a value later. So we've got a stretch factor, and then we have, if we have a single root, I'm going to write that one first. If we have a single root at 2, that means we have a factor in our polynomial of the opposite sign of this, so x minus 2. It's a single root, so this gets an implied power of 1. I'm not going to write that there. I'm just showing you it is a single root, meaning that it has a power of 1 here. And we have a double root at -3, so that means, remember, it's opposite of the sign, so x plus 3. And because it's a double root, we have a squared here. All right, off to the side here, realize we could also write this as y equals a x minus 2 x plus 3 times x plus 3. Okay, we could do that, but this is simpler, right? This is a simplified version, so this is what we're going to go with. All right, I would accept this, but this is actually a better way to actually write it. Okay, so let's just start filling this in. So we've got to put in this point now, right? We've got to find this a value here, so we need to substitute in a -4 for these x's and a 3 for that y. So I'm going to rewrite this as 3 for y equals the a value we don't know yet, and then substitute in the -4 for x here, substitute in the -4 for x here, and continue working this out. So we would have 3 equals a times -4 minus 2 is -6. -4 plus 3 is -1, and then that squared. -1 times -1 is +1. So we actually end up with 3 equals -6 times 1 is -6 times a. Okay, so we're going to divide by -6, and we get our a value is equal to -1/2. So our final equation ends up, or function ends up being y equals -1/2 x minus 2 x plus 3 quantity squared when we're all done. Okay, we found this a value, which we always have to do there. Now the last thing that we need to do is sketch this thing. All right, and that's pretty easy to do. We did that a lot in the first lesson. So let's go ahead and start by putting in the roots. So we have a single root at +2, so we'll put that in right there at +2. We know that we have a cubic graph, so we know our end behavior is that of a cubic graph, and we have a negative out in front here, so that's going to be our end behavior. I'll write it over here, is going to be up to the left and down to the right. So that's what our end behavior looks like. And we know that we have a double root at -3. So that's right here at -3. And that means it's either going to sit or bump on the x-axis. That double root, remember, it goes tangent to the x-axis but doesn't actually cross all the way through. Here we have to cross all the way through. We also know that we have the point -4, 3, so That's approximately right here, so I'm going to write that negative 4 comma 3. We know it's right there. Alright, so our end behavior is like this. So we know we are going up and to the left, so we know we have this going on, and we know we have to go through negative 4, 3. So it's got to come down like this. We know that negative 3 is a double root, remember. Okay, don't forget about that right here, double root. So we've got to come down and we're going to bump, sit on the x-axis right here. We know we curve up because this is a double root. If it were a single root, we would go all the way through. But this is a double root, so we're going to just sit on the x-axis like this. And then we're going to have to curve back down like that in order to go through our single root at x equals 2. And that completes our graph, and our end behavior is correct. It's up and to the left, down and to the right. All right, so that's approximately what this looks like. Again, this local maximum right here, we don't know how high that is. We don't know that exact point, but we do know this point, and we know we have double root at negative 3 and a single root at positive 2. All right, so let's put that in the calculator quickly. We've got the last one from the previous example in there, so always put fractions in parentheses. So negative 1/2 is our stretch factor, our a value, and then parentheses x minus 2, close parentheses, new parentheses, x plus 3, x plus 3, close parentheses, and that's quantity squared. Okay, let's graph this, and picture looks right. Now let's check in our table and make sure that we have a 0 at negative 3, a 0 at 2, and then the point negative 4 comma 3 also needs to be in our table. And we have negative 3, we have a 0 at negative 3, we have a 0 at 2 right here, 2 comma 0 is there, negative 3 comma 0 is there, so that's all good. And then we need negative 4 comma 3, and that's in there. So we know we did this correct. Okay, so that's how we use our calculator to check these. All right, one more example and this video will be done. All right, example 3, the last example for this video, says we have a 4th degree function. Okay, this makes sense. Look at the end behavior. It's that of a 4th degree. Okay, it's going to be a positive 4th degree function because of the end behavior. It's going up and to the left and up and to the right. All right, so that makes sense. And it contains the point negative 651, so negative 651 way up here, and has roots shown below. Confirm your solution with the graphing calculator. All right, so we need to identify our roots. Well, this one right here is obviously a single root. So we have a single root at x equals negative 1, 2, 3, 4. So x equals negative 4. And this one we can see we have a triple root. This is the root where we have a change in concavity. So right here we're concave down, here we're concave up. So that is a triple root. So we have a triple root at x equals 2. Okay? Alright, so we've got the roots and we've got a point, so we can write this equation. In this case, the graph is given to us, so we don't have to create a sketch. Okay? I'm going to go ahead and label this one x equals negative 4 on our graph here, and this root was x equals 2 here. Alright? Alright, so remember, we're going to have to identify the a value. That's the one thing we don't know yet. So it's y equals a stretch factor that we don't have yet, times, we can write either root first. It doesn't matter. I'm going to write the single root. So if the root is at negative 4, I need opposite of that sign, so x plus 4, and that's got a power of 1. There's an implied power of 1 here because this is a single root. Then we have a triple root at x equals 2. So I have to write opposite of this sign. So instead of x plus 2, it would be x minus 2. And then because it's a triple root, it needs a power of 3. Now remember, we could write this x minus 2 quantity cubed by writing x minus 2 3 times. So x minus 2 times x minus 2 times x minus 2. But this is the fastest way to do it right here. So I'm going to leave it in this form. Alright, so the next step is that we have to substitute in this point. So a negative 6 for my x here and here, and then the 51 will go here for this y in order to solve for my a value. So I'm going to rewrite this now, change colors here, so that would be 51 equals a times negative 6 plus 4 times negative 6 minus 2 all cubed. All right, so let's work that out. That gives me 51 equals a. Negative 6 plus 4 is negative 2. And then we have negative 6. Let me redo that. Negative 6 minus 2 is negative 8. And that's going to have to be cubed. So let's put that in the calculator over here. All right, so that becomes negative 8 cubed, so we need to put that in parentheses. It's still going to be negative 8 cubed. All right, so that's negative 512. I didn't want to try to do that in my head. So it's 51 equals negative 512. So it's negative 512 times negative 2, so that's positive 1024. So 1024a, divide by 1024, and we get an a equals 51 over 1024. We can probably approximate that as a decimal, so let's do that. 51 divided by 1024, and 0.0498 works. All right, so a value equals 0.0498. All right, so now finally I can write this equation, this function, y equals 0.0498 times, back up here now, x plus 4, and then x minus 2 quantity cubed, like that. One last step, let's check it in our calculator and make sure everything works out. So we have y equals, clear that one out. In order to make sure that all of my values work out, I'm going to go back to this fraction just to make it exact. So parentheses 51 over 1024. It would still probably round fine if I put in the 0.0498 there, but I'm going to stick with this fraction because I know that is exact. And then parentheses x plus 4, parentheses, new parentheses there, x minus 2 raised to the power of 3. All right, so let's graph that. Okay, our graph, that looks good. We've got the single root at negative 4, the triple root at 2. Now let's just check our table. So when x is negative 4, y is 0, that checks. When x is positive 2, y is 0, that checks. Now we need negative 6, negative 51 in there. Negative 6, comma 51 in there, and we have that, so everything is correct. All right, so we'll call this video complete. I will see you in the next video.